All right, so this is chapter 28, Life in the Universe. Okay, so some of this stuff is not really for Astronomy 101, but we'll just kind of skim through that material. That is the stuff about stars. All right, so cosmic. This is the general outline. Cosmic evolution, which is, we'll briefly touch on that. Viruses, life in the solar system, intelligent life in the galaxy. There's a thing called the Drake equation. We'll talk a little bit about that. And then, of course, the search for extraterrestrial life, which has actually been going on for a long time. All right, so let's look at the cosmic evolution. So the universe, of course, which is not part of Astronomy 101. When we think about what's called cosmology, the evolution of the universe certainly has been changing. Stars have evolved. I talked a little bit about this, even when we talk about planets and where do the different atoms of the periodic table come from? They of course come from dead stars, and then the dead stars are the seeds to next generation stars. In fact, our sun we believe to be a third generation star. That is, stars died, they seeded the galaxy, and then those stars died, and then they seeded the galaxy again. Anyhow, so when we look into on the Earth, for example, there are almost all the elements on the periodic table. All the stable elements that are on the periodic table. There's a couple of them that you don't find on the Earth just because they don't have any stable isotopes. Right? They're always radioactive, and the radioactive half-life is much smaller than the age of the Earth. So you're never going to find, for example, there's an element called technetium that doesn't have any stable isotopes. But for the ones, we don't need to concentrate on that. This is not a discussion of nuclear physics. But for the ones that the atoms that have stable, that is, they're not radioactive, we find all of them on the Earth, all the stable ones. All right, so let's see. All right, so what exactly are we looking for when it comes to different life forms? What must life forms have? This is getting a little into the area of biology, but we'll certainly tackle this. Certainly, a life form needs to be able to react to its environment, right? So that's a very basic thing. What happens in the environment? This of course involves evolution. It's part of the idea of evolution is that some kind of life form has to be able to react to its environment. All right, so they also, living things also need the ability to grow. That is, they take in nourishment, and somehow they have to be able to process energy. All right, of course, different life forms do that in different ways. Plants do it completely different than animals. All right, but again, this is not a lesson in biology. This is still an astronomy class. But in astronomy, we're certainly interested in what we find out there in the universe, particularly in solar systems for Astronomy 101. All right, so also there has to be the ability to reproduce. in some way. You know, whether reproduction involves parents or um, seeds or something like that. And then the final thing is that living organisms have to be able to evolve. That is, with changing conditions, changing environments, they have to change if they're going to survive. Okay, so that is absolutely essential. All right, so let's see what that is. So this is just the different epochs of the universe. Again, this is more in Astronomy 102 than Astronomy 101, but that's perfectly fine. We can certainly look at this. There was, of course, the Big Bang, and then stellar evolution. Stars began to form, and then galaxies, and then, of course, as I mentioned earlier, stars die, and then they seed the local galaxy with heavier elements, because, of course, the universe begins with just hydrogen and helium, and the heavy, very, very massive stars evolve very quickly, and they die, and they produce heavier and heavier elements. And then eventually you have stars that are evolving that have all the elements present in them, and of course that happened about 4.6 billion years ago with the in our solar system, and then about 3 billion years ago we believe that there was life on the Earth. All right, so let's go through that a little bit, because that's really all we know about. Let's see. So, in the first billion years of the Earth, we really don't think that there was life, or if there was, it probably, if it did come about, I mean, there's some theories about this where, life evolved and then, life formed on the Earth and then died out in various catastrophes. I mean, we know that the Earth underwent massive changes in the first billion years of its existence. Anyhow, there were in the first billion years or so of the Earth's existence, we know that the volcanic activity was going on. There was hydrogen produced, nitrogen, and carbon compounds. Okay, so as it says right there. So as the Earth cools in the first billion years or so of its existence, there is in the very early atmosphere methane, ammonia, carbon dioxide, and of course water vapor. Eventually, when the Earth cooled enough, there's liquid water raining from the sky, and let's see. So, and we think that very, very quickly after that early atmosphere formed, that there were lightning. There was lightning and also ultraviolet radiation taking place, ultraviolet radiation penetrating the atmosphere, because there was no ozone layer, right? The O3 molecules in the upper atmosphere wasn't even present, and so any ultraviolet radiation would have made it to the ground. Also, of course, during the early years, the first billion years or so of the Earth's existence, there was a very heavy meteor activity. Of course, there's still meteoroid activity. Meteoroids are just when meteors are large enough to actually hit the ground. That was certainly much more active. That is, meteoroids hitting the Earth in the first billion years of our existence. than is currently going on. I know I already said that. All right, so over a billion years or so after the Earth forms, and we think that this really happens about 3 billion years ago or so, or at least we have evidence of life forming about 3 billion years ago. It could possibly go back a little bit more than that, but we definitely have fossilized evidence. All right, so we'll go into that in just a little bit. So we think that about a billion years ago, we get amino acids and then nucleotides that are forming. So amino acids, of course, are the building blocks for proteins, right? Absolutely essential for any life form on the Earth today. They all use amino acids and they all use proteins. Back in the 1930s, let's talk about this experiment. This was actually a very significant experiment for biology and of course for astronomy as well and chemistry. It's called the early Miller experiment, and it was, as it says there, it was the very first time it was performed, and it's been performed multiple times since then. Basically, what we did is, early Miller did, is they filled up a container of glass with various gases that we thought were in the early days of the Earth, or in the Earth's atmosphere. Nitrogen, for example, the N2 molecule, carbon dioxide, methane, and ammonia. And what they did is they said, okay, well let's put sparks and see what happens to this gas. And lo and behold, they noticed something very interesting. There was the formation of some amino acids in this very early in this experiment, and that was actually really surprising at first. I mean, people thought maybe that was what was going to happen, but to actually see it happen and to be able to go in there, with microscopes and identify these amino acids was pretty significant. All right, let's see. So in this image, we're seeing some protein-like droplets that form from clusters of many billions, as it says, of amino acid molecules. So these are various amino acids, and these things split and they form smaller droplets, as it's showing right here. All right, and so one of the things, this is what I mentioned about the evidence that we have for life forming. And remember, this is under an extremely small scale, right? So this is we even need electron microscopes to see this small of a scale. Anyhow, on the left-hand side is fossilized evidence. So this is about 2 billion years old of single-celled creatures. And on the right-hand side, that's modern algae, right? So they look very, very similar when you look at these two pictures. You can kind of see the very strong similarity between the two. All right, and then let's see. So, the question is it possible that the source of complex organic molecules could form outside of the Earth, on meteorites and so these are meteors that are traveling through the solar system, or even comets. And we've actually found that on comets and meteorites, that there are these